So in this video, we're going to talk about SF4, and we're going to ask ourselves, is this molecule polar or is it non-polar? Well, the first thing we're going to do is draw the Lewis structure. So I have a sulfur and I have 4 fluorine atoms. I look at the periodic table, I know that sulfur has 6 valence electrons. It is oxygen's cousin, and I know that fluorine gives me 7 valence electrons. So the total number of electrons I have to place would be 4 times 7 because I have 4 fluorine atoms, 7 each, that has 7 valence electrons each. So 4 times 7, that should be 28, right? So we have 28 electrons from just the sulfur, from the fluorine, plus 6 from the sulfur, right? So we should have a total of 34 electrons that we have to place. Now, so usually, again, in molecular formula, usually the atom that's furthest to the left in the molecular formula will be your central atom. And so we could safely place our sulfur in the middle. And at this point, I'm just going to surround the molecule with 4 fluorine atoms. All right. So at this point, I'm just going to start to build using single bonds. So I could form a single bond between all my fluorine atoms. At this point, my sulfur has 8 valence electrons. Now remember that sulfur is one of those atoms that can have an expanded octet. So if you have more than 8 electrons around sulfur, you shouldn't be alarmed. Right? That's totally possible. Now we have 8 valence electrons, so let's leave sulfur for a minute, and let's try to fill the fluorine's octet. So we have in this fluorine at the bottom right, we have only 2 valence electrons around it. And we said that we're going to leave sulfur for now. So we could start placing lone pairs around the fluorine atom. And that will give me 2, 4, 6, 8. I could possibly do the same for each and every one of these fluorine atoms. And let's see how many electrons we have actually placed. So at this point, all our fluorine atoms octet is satisfied. Now we have 8 electrons around. We have 8 electrons around each of the fluorines. So 4 times 8, that would be 32 electrons. So just looking at the molecule right now, we have 32 electrons. And we need 34, so we're missing 2. All right, so the only other place, since fluorine's octet is full, for us to put the 2 electrons would be on the sulfur, and this would be in a pair of lone pairs. Now, to determine if this molecule is polar, you really have to get the geometry right. Now, if we just look at this structure like this, and we draw our dipole structures, so let's look at this and draw our dipole structures, then we know that fluorine is more polar than sulfur. So the atoms, or the electrons, should be hogging the fluorine atoms. All right, and so if we draw our dipole moments, you would actually see that these look like they're canceling out because we're having tail-to-tail dipole moments. But the geometry is incorrect. What happens is that because we have these pair of lone pairs, it actually shifts the bond angles down, and so this molecule is actually a seesaw molecule. So if we redraw our structure, what we do have, and so if we redraw our structure the correct way, because of the lone pairs that change the bond angles, and typically, as a rule of thumb, when you want to get good at drawing determine if molecule is polar or not, the minute you see a lone pair on your central atom, you should think polar. Now, it's not always the case, but majority of the time, if you have a lone pair in the central atom, even if all the substituents, even if all the groups surrounding the central atoms are the same, usually if you have a lone pair in the central atom, your molecule is going to be polar. So really what we do have is that these lone pairs actually bring these bonds closer together. And so what we do have is a molecule that looks like this, what we call a seesaw geometry. And so this is what we really have in terms of SF4. Now, like I said before, you could draw the molecule like this, but you would have to realize that because you have the lone pairs in the middle, then that would make your molecule polar. But I'm drawing this to show you the correct geometry. If we actually then redo our dipole moments, what we do see is that the top and the bottom dipoles, as in my structure, cancels out. And we also have dipoles going from this sulfur to the fluorine, and this sulfur going to the fluorine. Now, if you've seen the videos, you know that anytime you have, for example, dipoles going in slanted directions, then the net dipole moment would be down the middle, right? So this would be the net dipole moment, right? And it's the same thing if it's going upward, right? If I have dipole moment going like this way and I have a dipole moment going like this way, then the net should be straight up the middle, right? And it's the exact same process here. So using these markers, if we draw our dipole moments, I'm just going to redraw them, then what we do have is a net going this way, right? So the net dipole moment is actually this red arrow, right? So remember the top and the bottom fluorines, these cancel each other out. So the only other dipole we have in the moment is this red arrow. And so the molecule does have a net dipole moment, and so that's why SF4 is actually polar, right? So the correct geometry is good, but as I said before, you could just guess that this molecule is polar just by having the lone pairs. But to do it the correct way, you have to get the geometry right, and this is how SF4 is actually a polar molecule.